This is MATHguide.com, and my name is Mark Karadimos. Alright, so in this video we're going to figure out how to do a related rates problem as it applies to a ladder. So here I've got a problem that says I got a 17-foot ladder, it's up against a wall, and it's sliding. Okay, so what I'd like to do is draw a picture of what's happening so we could understand. This is a very common problem in calculus. So here's the wall, here's the floor. Wow, I'll never draw it that straight ever again. Okay, and let's say I've got a 17-foot ladder. Okay, so there's this 17-foot ladder, okay, resting up against the wall and the floor. So it's 17 feet. So I'm going to put that in there. Okay, and they give us some information. When there's 15 feet from the wall, what's happening? Anyway, so what's happening is the bottom must be slippery. The floor must be slippery because the ladder is kind of sliding down. Okay, so that means that the top of the ladder is sliding down the wall, and the base of the ladder, the bottom of the ladder, is moving away from the wall. So it's moving this way. Okay, so I know kind of what geometry is happening here with the ladder. Okay, so I'm asked to do some things. Now, before I put the number 15 in here, let's talk about that. There's some things that are constant in this problem. There's some things that are changing. The shape of the ladder, we're assuming, is going to be fixed. So that ladder is always going to be 17 feet. Now, the distance the base is from the wall is not going to be the same. That's sliding. So I know that this distance, which I'm going to refer to it as x, is going to be changing in our problem. And I know that the top of the ladder is sliding down the wall, so this distance is changing also. Okay. I'm also going to assume that there's a right angle here between the wall and the floor, which is a pretty safe assumption. Okay, so what's the relationship between the horizontal, the vertical, and the ladder length? Okay, well, it's real simple. It's good old Pythagoras. X squared plus y squared is equal to 17 squared. All right, pretty simple so far. Okay, well, now before I could plug in any information into this, because here you're talking about rates. There's no rate in this diagram. There's only distances. So this is where the calculus comes in. What I'd like to do is to take the derivative of the left side with respect to time and the derivative of the right side with respect to time. Because here I'm talking about rates, distance as it applies to time. So I'm going to take the derivative of this entire expression, left and right side, in other words, the entire equation. Okay, so if I take the derivative of the left side, well, it's just going to be the power rule and the chain rule combined. So the derivative is 2x, but the chain rule says I also have to take the derivative of x with respect to time. Okay, then it says, well, let's see, the power rule says I have to take 2y, but then I have to take the derivative of y with respect to time. Okay, then I got to take the derivative of this. The derivative of that is 0. So 289, derivative of a constant, no matter what the number is going to be 0. Okay, so I've got some relationships here. Now I've got some rates, and I can figure out what's going on. Okay, now what I'd like to do before I move forward to actually trying to plug in information into this and try to solve for part 1, I want to move some things around, give myself a little space. So I'm going to move this in the top right corner. All right, so let's now try to figure out what this given information means. I would call this step 0. Before we even get into trying to solve the problem, let's get our base information, our initial information set. So when the base of the ladder is 15 feet from the wall, okay, that's the distance here. That must be referring to the distance x. It's 15 feet. All right, then what? The base of the ladder, okay, that's the bottom of the ladder, is moving at 3 feet per second. That must be Let me put it over here, scrap for time. That's how the x distance is changing with respect to time. And I'm going to call that 3 feet per second. Okay, that's step 0. We define our variables. Okay, now we could get into step 1. Okay, step 1 says, how fast is the top of the ladder moving? Okay, what are we being asked to find? We're trying to figure out how the top is moving, not what the distance is. It's not asking for y. It's asking how fast it's moving. That's a rate. That's dy dt. So they're asking us to find dy dt. So we go, don't know what it is. Okay, well I could do a lot of algebra here to now solve for dy dt. Let's hit the easy button. Okay, hit the easy button and let's solve this by plugging in what we know first. So I'm going to plug in, let's see, x is 15. I know that dx dt is 3. And I'm going to put 2 times y. Oh, what's y? Now you're thinking, how could I do this problem? I don't know what y is. I don't know what dy dt is. I have one equation. I got 2 unknowns. Not so fast. Okay, we really do know, or at least we can calculate what this y value is. Now keep in mind that our x value is 15. So what I'm going to do is plug in 15 here, and I'm going to do some Pythagorean theorem, right? I'm going to take y squared plus 15 squared is equal to 17 squared, and do a little, and let's get y. Okay, so I'm going to do that. What's the answer? And it's 8. I am not going to show that. It's Pythagorean theorem. dy dt equals 0. Oop, almost made a boo-boo there. Okay, so here you have your setup. Everything's plugged in there. Of course, we're trying to solve for dy dt. I'm going to just clean this up a little bit. Think of this as negative, 30, that's 90. Getting ahead of myself. Okay, and this is 16 dy dt equals 0. Okay, now how am I going to get the dy dt alone? Well, I'm going to subtract 90 and divide by 16. Okay, so a little bit of algebra there. I subtract 90 and divide by 16, which is equal to, if I look over by my handy dandy calculator, it's negative 45 eighths. Of course, this is feet per second. This is a rate, right? Feet per second. Or if you prefer, we could write this as negative 5.625 feet per second. Okay, there you go. So we now know what dy dt is. So I'm going to add that to our list up here. Okay, and I'm going to move on to problem number 2. Okay, so I moved all the information up there, so I got it all in one tidy spot. Earlier, just a moment ago, I had this as approximately equal to negative 5.625, meaning, of course, that the ladder is moving downward. That's what the negative represents. I don't know why I had approximate there. It's exactly. I didn't round anything. Okay, anyway, let's move on to part 2. Part 2 says, at that moment, what is the area? How is the area changing? So, of course, when they refer to the area, they're referring to the ground, wall, and ladder. So we would say all of this, put a little, maybe a color in here. So we're referring to all of this area inside the ladder. Okay, so how do we get that area? Well, let's start talking about the area. So area, A, is equal to, since this is a triangle, it's 1/2 times the base times the height. All right, easy enough. Again, I want to know how the rate of area, how the area rate is changing. Area itself is just a number. This isn't a rate. So again, we've got to take the derivative of this with respect to time, because I want to see how it's changing at that moment in time. Okay, so I take the derivative of the left, dA dt, with respect to time. I take the derivative of the right with respect to time. Now, I'm really looking at these two, since the area is changing, and that means the x and the y is changing, which makes the area change. So these are not constant values. These are two different variables. So I have to now do the product rule. And of course, I'm looking at the half, not doing the product rule with the half. The half is outside of the derivative. So in other words, I'm taking the derivative of this inside and looking at this as it's a product. Okay, well, you take the x, and then you take the derivative of y with respect to time. Then you say, I've got y, and take the derivative of x. Whoops, boy, I'm getting sloppy there. Derivative of x with respect to time. Okay, there you have it. So that's what this relationship looks like. All right, well, let's plug in what we know, because I want to know what the rate is, right? So actually, I didn't do this, but this is part 2. All right, so how do we do this? Plug in what you know. Okay, so let's plug in what we know. We know what x is. It's 15. I know what dy dt is. Just figured it out. It's times negative 5.625 plus y. Oh, you know I erased that? It was 8. That's right. I did not write that in there. But after we did the Pythagorean theorem with 15, we found that it was an 8, 15, 17 triangle. I should put that down. We did that earlier. Okay, so we know that this is 8. And we know dx dt. dx dt is 3. All right, so all you got to do is plug this into a calculator, and the calculator will give us the rate. And the handy-dandy calculator says this is exactly equal to, and just looking over here at the calculator, negative 30.1875. And now what is the area? This would be square feet. Right, that's area. Area would be, since I've got feet, the area must be square feet. With respect to time, my time here is in seconds. And there you go. So I now know that the area is about, it's changing, shrinking, right? The area is shrinking by 30 square feet per second. Okay, there you go at that particular moment. All right, so please make sure you like the video. Please subscribe to the channel. I would really appreciate it if you did that. And make sure you go back to MATHguide.com, where we literally have hundreds of lessons, interactive quizzes, and instructional videos. Take care. Well, you really could use a ladder to get a leg up on the world, couldn't you? Could you rise above the fray? Oh, there's too many jokes.